Welcome everyone. My name is Asif Ahmed, Assistant Professor at State University of New York, Sony Polytechnic Institute, and with me,
I'm Mohammad Sadiq Khan, Assistant Professor, Jackson State University.
we are the session chair and co-chair for this session. This session is titled Roadways. We'd like to thank Tensor for generously sponsoring this session. We greatly appreciate their support. A couple of things to note before we start the presentations. You'll have the opportunity to ask questions during this on-demand session by clicking the questions button at the bottom of the video window. Your questions will be sent directly to the presenter to answer as soon as they are able.
To claim PDH credits for this session and any other education session, you simply need to click on Claim Credit button on the conference homepage. From there, you'll fill out the survey for any session that you attend. Please note that you will need to include the verification code shown in this session to verify that you did attend the session and ensure that you receive the proper credits. Please enjoy the presentation.
Enjoy it.
Hello everyone, my name is Debojit Sarkar and today I'm going to talk about the inverse analysis method on the performance evaluation of geosynthetic reinforcements in highway pavement on expansive soils. The research was conducted with my supervisor, Dr. Jay Wang. Let me go through my educational background first. I did my Bachelor of Science degree in Civil Engineering from Bangladesh University of Engineering and Technology. I did my Master's in Civil Engineering from Louisiana Tech, and right now I'm a PhD candidate in Materials and Infrastructure Systems Engineering in Louisiana Tech University. So this is the overview of my presentation. First, I'll go through some introduction, then I will talk about the analysis of geosynthetic reinforced pavement on expansive soils. Then I'll go through the performance evaluation process of geosynthetics, which is an inverse-based method. Finally, I will show a parametric study considering the influence of shear stiffness of geosynthetics. Then I will show the overall concluding remarks and finally the acknowledgements part. In United States, billions of dollars are spent every year to solve the soiling-related stresses on the highway over expansive soils. So this is typically not feasible to avoid these soils because of the widespread distribution everywhere all over the United States. These soils show volumetric changes because of presence of soiling minerals such as montmorillonite that soils or shrinks with the fluctuation of moisture content. This figure shows how the soil is dried and create cracking on the surface of the soil just because of the shrinkage effect of the soiling soils such as the expansive soils. This figure shows the approximate distribution of major montmorillonite clay deposits in the United States. You can see from the figure there are some parts such as the Texas, some part of Louisiana, and even some of the west coast. Actually, there are a lot of montmorillonite clay minerals available on the ground. The highways constructed on these expansive soils, these are subjected to the differential movement with seasonal drying and wetting. Because of this, they can cause heave or shrinkage, which ultimately results in development of cracks that are literally found on the surface of the pavement. In the figure, you can see the most longitudinal cracking developed because of the expansive soil is either on the shoulder of the pavement or along the center line of the pavement cross section. To fix this segment of the highway, mechanical system using geosynthetics can moderate the uplift pressure from the expansive soil subgrade and can protect the pavement surface. Because the pavement structure is good in compression but weak in tension, so engineers added geosynthetics in the layer to supplement this limitation of the pavement. So a lot of research has been led to understand the effect of the traffic loads on the performance of the highway where geosynthetic is put on the pavement layers. However, the performance measurement is not available to understand the effect of the environmental loads, such as those resulting from the subgrade volume changes. So many researchers have proposed characteristic models to simulate the behavior of reinforced pavement. However, all the researchers was concentrated on a common forward problem. So the forward problem means the where we apply a load on the pavement, or pavement is considered as a beam, and we see the how the shear force or bending moment changes within the structure. So, but in our case, the pavement deflates not because of the external load, but due to the fact that the subgrade volume is changing. So we have to calculate it through inverse based method. So in this study, we analyzed the geosynthetic reinforced pavement using the beam theories. So, so some steps through the process to analysis of geosynthetic reinforced pavement on expansive soils could be the application of the beam theories for analyzing the pavements on expansive subgrade soils. Then we'll take the Timoshenko beam theory to analyze the geosynthetic reinforced pavement on expansive soils. So there's a new concept we developed, which is called the virtual load concept. So this inclusion of the concept of virtual load, this will embrace the heave or shrinkage deformation of the pavement in the beam theory, and then make the Timoshenko beam on Winkler or Pasternak foundation model applicable to expansive subgrade soils. So the model has been established and built in MATLAB, and this can be employed for different case studies. So we used a case from Texas Roadway Farm to Market 2. So for the analysis of the reinforced and non-reinforced section for using this model. So this is the schematic diagram of one-dimensional loaded beam. So the beam is considered as a reinforced Timoshenko beam, and which is overlying on soft soils, which is mimicked as springs. The foundation or the spring foundation, which is modeled using the single parameter model such as Winkler foundation, or we can use the two parameter models such as Pasternak foundation model. So here the to represent the soil, we use the parameter Ks, which is the spring constant or the modulus of subgrade reaction. Here with the blue marker, the geosynthetic is marked with the red line, and you can see figure 4b, which is the sign convention on the beam element, where you can see the load Q, which is an arbitrary pressure applied on top of the beam, and the reaction force Ks times the deflection of the beam W, which is acting on the from the bottom side of the beam element. So we have four boundary conditions, like since this is like free end beam, so we have the moment and shear which is 0 at the starting point and the end point of the beam. So what is virtual load? That's the first question. So virtual load model was developed by Dr. Adnan Khan during his PhD dissertation research at Louisiana Tech University. So virtual load is not a real load, but is the load which causes the pavement deflection equivalent to the heave or shrinkage induced deformation from the subgrade. So from figure A, we see a pavement on non-expansive regular soil where external load is applied on the pavement, and in figure B, the pavement deflection due to that external load. In figure C, we see the pavement deflection due to the expansive soil, so there is no external load. So we will try to calculate the equivalent load that will cause this amount of deflection. So in figure D, you can understand the proposed virtual load soil model, where the virtual load is causing the equivalent deformation from figure C. To understand the performance of geosynthetic reinforced pavement, we developed the inverse based method. So first we have to understand how these longitudinal cracks are developing on the pavement. So during the rainfall, the moisture content increases in the subgrade, or during the summer, the moisture content decreases. So since this is an expansive soil, and because of the moisture content fluctuations, its volume is changing, either it's increasing or decreasing. So it causes differential movement, and then these longitudinal cracks happen on the pavement surface. Since we cannot measure directly the deflection from the field, but the researchers did a lot of research in the field to calculate the moisture content by putting the moisture sensors underneath the pavement. So we use simple 4 steps to describe the inverse method process. So first we get the moisture content measurement data from field. Here in the figure you can see in the cross section of the pavement. So we have measurement at W1, W2, W3, etc. through Wn. So we will measure this moisture content data, or we can get the moisture content data from the field. Then we can use the empirical equation to get the deflection because of that moisture variation. Then number 3, we use the load Qx, which is a Fourier series, because using Fourier series we can describe any type of load such as line load or distributed load. Since this is a non-uniform distributed load, so Fourier series will give us the realistic results. So finally, we will use the linear least square method to find the virtual load parameter and get the virtual load Q. So this study, we are investigating the geosynthetic reinforced pavement, which is like simplified as a reinforced Timoshenko beam on an elastic foundation. So we will study this by selecting a group of parameter, which is shown in table. So these are obtained from previous literature. So what happened was, like in the previous literature, they applied a load of 1000 kilopascal on the pavement to finally calculate the deformation. Since our model will take the deformation as an input, we will back calculate the load and see if it gives the exact same load that was applied in the first time. So in this way we can get the verification of the model, and finally we can be able to calculate the bending moment and the shear forces using our model, and then we can apply it for realistic case studies like in the roadway in Texas FM2. Here in this figure, you can see the red line, which shows the deflection from the given load Q when it's 1000 kilopascal, and using the forward analysis method. So when we use the linear least square or the inverse analysis method, so we get this blue line, which is pretty much close to the deflection coming from the forward method. Since we are applying the load as a Fourier series, which is unknown, and we know the amount of deflection coming from the pavement, so the Fourier constants have to be calculated using the inverse method. So all the Fourier constants which are regarded as a reinforced pavement foundation system parameters, right? So we see that the number of Fourier terms taken in this study actually affects the convergence of the bending moment of the shear force of the beam. So here we show the amount of load we are getting from the back calculation. So this black line represents the external load, and the other lines representing the virtual load depends on the number of Fourier term used. Since we increasing from 4 to 8 to 15 to 100 and getting closer to the actual external load that was applied on the first time. So this is the shear force distribution along the cross section of the reinforced pavement. You can see the black line represents the shear force that was calculated using the forward method for the applied load, and other lines representing the shear force that was calculated using the inverse method. This at the beginning and the end of the pavement or the beam, you can see the shear force actually converges pretty well. But the number of Fourier terms didn't affect much on this case. So this is the distribution of moment along the cross section of the reinforced pavement. Similarly, the black line here represents the moment distribution coming from the forward analysis, and all the other colored lines are representing the moment distribution from the back calculation or the inverse analysis method. Since we use linear least square, and we can see here depending on the number of Fourier terms used, the moment converges or it doesn't converge at the beginning and end of the pavement. So we propose the solution with the red line where the moment converges at the beginning and end of the pavement. After we are able to get the results, now we will move forward to do the parametric study where we will show the sharing stiffness, the effect of sharing stiffness of geosynthetic on the performance of the pavement. So in the figure 11a, you can see the deflection is same for the different sharing stiffness of the geosynthetic. So if we use the same amount of deflection and we change the sharing stiffness of the geosynthetic, so the virtual load will vary. So here two line and one blue and one red line representing the two different type of synthetics which consider the sharing stiffness. Here the full G sub G defines the where the sharing stiffness is considered, and the 0 G sub G defines where no sharing stiffness is considered. Since geograde is type of geosynthetics which can take some sharing force, but geotextile is a form of geosynthetic which do not carry the shear force. So we can say like full G sub G is for geogrid condition and 0 G sub G is for geotextile condition. So from this virtual load, we can see how it varies with the geogrid and the geotextile conditions. So here we present the results for varying the shearing stiffness of geosynthetic. We are presenting the results of rotation, shear force, the moment, and most importantly, the tension in the geosynthetic reinforcement. So by varying the shearing stiffness, we can see if we consider the shearing stiffness, the tension, and we see the tension diagram, we see the for the geogrid case or the case where we consider the shearing stiffness of the geosynthetic is taking much more tension for the same deflection than the condition where there is no shearing stiffness considered in the geosynthetic, right? So which concludes that geogrid will take much more load, or it will withstand much more deflection in the case where the deflection is coming from the subgrade. So here are the concluding remarks of the whole presentation. So we designed a methodology for geosynthetic reinforced pavement on expansive soils by integrating the volume changed induced deformation of the subgrade that was introduced. So then we applied the Timoshenko beam theory to evaluate the structural performance of geosynthetic reinforced pavement on expansive soil. So, and another concluding part is measurement of for superior performance of geogrid over geotextile to moderate the uplift pressure from the expansive soil subgrade to protect the pavement surface was also introduced. So I would like to acknowledge some of the people and the institute. Because of them, this research was made possible. So this research was done at Louisiana Tech University, and this was sponsored by the Southern Plains Transportation Center. And this research was supported by a fellowship from Geosynthetic Institute. So that would be all. If you have any questions, you can just send me an email. Thank you so much for your attention.
This presentation is about a state-of-the-art large-scale laboratory approach to evaluating the effectiveness of geogrid reinforcement in flexible pavements. The presentation is provided by Hossein Ali Mohammadi, Vern Schaefer, Junxing Zhang, and Guangfang Zheng from Iowa State University, David White from Ingeus Geotechnic Incorporation, and the research is based upon a work supported by Minnesota Department of Transportation. Presentation outline includes introduction, test section configurations and sensors, procedure for performing the tests, results and analysis, and conclusions. Introduction. Geosynthetics offer a solution for reinforcing, stabilizing roads, and can improve performance of pavements against these stresses according to their mechanism of functions. These mechanisms are lateral confinement, increasing bearing capacity, separation, and tension membrane. Many experimental tests, including full-scale tests and laboratory tests and numerical modeling studies, had been conducted by many researchers. The results of previous experimental and numerical studies showed that some benefits of geosynthetic reinforcement are: extend the service life of pavement, reduce the thickness of base course layer with same performance, improving base course and subgrade stiffness by increasing their resilient modulus, provide performance effect on the base, and decreasing base course thickness by increasing resilient modulus, stabilization effects on subgrade by decreasing permanent deformation on top of subgrade, providing better distribution of loading, and delay rotting development, plus increasing the number of load repetitions until failure. Appreciable improvement of geosynthetic reinforcement depends on factors such as subgrade stiffness, base aggregate thickness and quality, hot mix asphalt thickness and quality, geogrid stiffness, location, and so on. This research will find what is current granular equivalent GE factor of geogrid using traffic benefit ratio and base course reduction. Traffic benefit ratio is number of load cycles reinforced over unreinforced for particular permanent deformation, and base course reduction is base thickness of reinforced over unreinforced for a given traffic. Minnesota Department of Transportation is assigning GE as 2 inches to geogrid reinforced. A large-scale experimental test plan was developed by using IMAS equipment to evaluate the reinforcement effects of geogrids on the structural benefits of pavements. A total of 8 test configurations were constructed by varying geogrid types, geogrid location in the base course, and base aggregate thicknesses, and the effect of these variables were studied on the resilient modulus, deflection, and permanent deformation results of pavement foundation. The test configuration, procedure of the test, and some details of performed tests and results discussed in the following sections. As mentioned before, the main parameters and factors studied in this investigation included base course thicknesses, position of geogrid, geogrid stiffness, and geogrid type. The IMAS system was developed to mimic field loading conditions of roadway systems in a large-scale laboratory system wherein the conditions can be more easily controlled. The IMAS performs a cyclic load test with a large number of load cycles, which simulates vehicle loading conditions on the pavement foundation. The IMAS can also help determine the resilient modulus, deflection, permanent deformation of the pavement, so that the pavement system's service life and the long-term performance of the pavement structure can be evaluated. Boundary effects and simulation of the natural soil's stiffness are controlled throughout the use of rigid walls and a foam layer. The thickness of foam layer was chosen according to the foam material's elastic modulus, soil properties, and realistic boundary deflection during the loading to simulate the effects of a boundary condition in the tank. 3 instrumentations were selected according to the literature review, the data type, and the cost. The LVDTs was used to measure the deformation happened on the pavement. The strain gauges was used to measure the strain behavior on the jaw grid rib, and two pressure cells were used to record the pressure. Steps of setting up the strain gauges on jaw grid are applying the top coat liquid on the strain gauges, adding foam tapes as protection, protecting the strain gauges wires by passing them throughout a plastic tube, setting the jaw grid on their positions, setting up the data logger software, compacting the base layer with plate compactor for 3 minutes, and simultaneously recording the strain gauges and sensors results to measure the effect of compaction on the mobilization of the jaw grid. A novel pattern of loading applied in this research is based on the random loading according to the concept of vehicle load distributions used in the pavement design for various vehicle classification in Mechanistic Empirical Pavement Design Guide MEPDG. For each test, the load was provided to the IMAS by a 305 mm diameter loading plate sitting above the center of the container. For each test section, to simulate the real traffic loading, 100 different loading shape patterns were assumed and randomly selected during the tests. Although the loading pattern is random, the distribution followed the same standard for each test. Totally 100,000 cycles of loading were performed in each section with a cyclic load pulse time of 0.15 seconds and a double time of 0.85 seconds. Each test took approximately 17 hours to conduct. The subgrade soil was added layer by layer. Each layer was less than 380 mm high to reach a uniform condition. A 23 kg drop hammer or compaction soil hammer was used to provide compaction after adding each layer. After leveling the surface, a 6.5 HP plate compactor was used to provide the compaction on the base layer for 3 minutes. A double layer of steel simulated the asphalt surface was used, which provides an equivalent weight of the real asphalt surface. To make sure the jaw grids at the interface position will get the maximum involvement and interlocking with the aggregates, a layer of aggregate with a thickness of 1 inch has placed at the top of the subgrade surface. Then the jaw grid was placed at the top of this thin layer, and then base material were placed and compacted in the tests. Results and analysis. From the results, it can be seen that during the application of compaction loads, the results of strain gauges in biaxial jaw grid have fluctuation and reach higher peak values than triaxial geogrids, which gradually increase to get the maximum value of strains. Also, the residual strain in triaxial geogrids is less than biaxial geogrids. Two pressure cells were used for each test, one located on top of subgrade and the other located on top of geogrid in the base aggregate layer, to measure the value of pressure developing in both aggregate and subgrade layers in the tests. The test sections have similar trends. The earth pressure cell data was increasing as the loading occurred, both in the subgrade and base course layer, but the increasing rate and magnitude are higher in the base course layer than subgrade layer. Permanent deformation results. From the results, it can be seen that triaxial geogrids perform much better than biaxial geogrids in reducing the permanent deformation of the sections for the same cyclic load numbers. Conclusions. From permanent deformation versus number of loading cycles plot, it can be stated that deformation of control section without geogrid reaches almost 1 inch at the end of test. However, triaxial and biaxial geogrid reinforced section deformation curves show a maximum deformation around 0.25 and 0.5 inches respectively, which is almost 1/4 and half of unreinforced section deformation. Generally, it can be stated that triaxial geogrid performs better than biaxial geogrid in decreasing permanent deformation of the pavement. Test sections with heavy-duty geogrid always have higher pressure cell readings than the light-duty geogrid. Also, since the heavy-duty geogrid having a higher stiffness than light-duty geogrid, the high-strength geogrid provides more confinement pressure as well. For overall earth pressure cell results, expect for GE4 and GE7, the test sections have similar trends. Earth pressure cell data was increasing as the loading occurred, both in the subgrade and base course layer, but increasing rate and magnitude are higher in base course layer than subgrade layer. This evidence supports that the geogrids can stabilize both subgrade and base course layer, but more in base course. GE4 and GE7 have a converse result, and the reason may be caused by geogrid location. Average air pressure cell data in triaxial geogrid test is higher than biaxial geogrid tests. The comparison between test section GE1 and GE4 on earth pressure cell data overall shows that under the same location and same thickness of the base course layer, the pressure in section 4 in the base course is at least 2 psi higher than the pressure in the section GE1 on top of subgrade layer. Triaxial geogrid would have more effectiveness than biaxial geogrid. Thank you so much for your consideration and time.
Hello, everyone. If you're hearing this recording, that means you're residing in the universe where I managed to get under the time limit, so that's good. Our presentation today is life cycle cost analysis of geotextile separator layer in low volume secondary pavement. So let's get to it. My name is Chaz Weaver. I am the District Materials Engineer for the Virginia Department of Transportation in our Stanton District. And my partner in crime is Audrey Maruza, research scientist at the Virginia Transportation Research Council located at the University of Virginia. A few years ago, the VTRC began a study to research aggregate contamination by subgrade fines. Over the years, our maintenance operations have caught distresses such as the ones in the left picture here. That is a secondary pavement in Virginia. And in the wheel path, you can see the alligator cracking and rutting and the fines that have actually migrated from the subgrade through the subbase aggregate layer and to the surface of the roadway. In the picture on the right, that is Interstate 81. It is a severely high amount of truck traffic. And although we have 14 inches of hot mix asphalt there, even though we have that much structure, you can see the subbase aggregate layer below the asphalt has been completely contaminated over time by the subgrade fines because there was no separator there. Being that we're at the Geotextile Conference, I think we can all agree that this happens in practice. The 8-inch clean stone that you designed and constructed is not necessarily there 30 years from now, depending on your subgrade conditions. But our current pavement design methods do not take this into account. So part of our VTRC study was to use an innovative life cycle cost analysis that we'll be talking about. So the first step in our life cycle cost analysis is to develop the two different pavement structure cases. We used VDOT's standard pavement design method, which is 1993 AASHTO. The parameters in the table, for the most part, are VDOT set parameters. The ones that are varied for our cases are the 155 annual daily traffic and the 1500. The 155 ADT case gives us the thinnest pavement for a secondary roadway. That is 1.5 inches of asphalt overlaying 8 inches of aggregate. The thicker, the 1500 AADT with 5% trailer trucks and 1% single unit trucks gives us a very thick pavement for a low volume secondary road. And that is 6 inches of asphalt over 5 inches of aggregate. You also note one of the variables at the bottom, subgrade resilient modulus. In 1993 AASHTO design, that equates to a CBR of about 3.3. In a conventional life cycle cost analysis, the maintenance activities are prescribed. In other words, you may be required to do an overlay in year 15 or reconstruct the pavement in year 30. The innovative portion of this life cycle cost analysis is that we're trying to incorporate the contamination and of the aggregate layer and the deterioration of the asphalt layers in more of a real world situation. So the top two graphs show the contamination of the aggregate layer, two different methods. One on the left, structural coefficient, and the one on the right, the remaining layer depth, or the thickness of the remaining aggregate layer. And basically in AASHTO 1993, you can see these are the same thing. So for efficiency's sake, we chose to go with the remaining layer on the right. The bottom two graphs show the idealized deterioration of the asphalt layers. On the right, almost mimicking the AASHTO 1998 pavement design guide, you see that there's a great fall off at the end. Those are for the surface structural coefficient. For base and intermediate layers, anything below the surface, we know that it doesn't fall off at year 20. Even though it's a 20-year pavement design life, it doesn't actually do that. You don't really, even if the asphalt layer is stripped and delaminated, you don't get a zero structural coefficient. So this is the idealized curve for different contamination rates. In 2019, PennDOT released a study where they measured the migration of fines into subbase using cyclic loading. So this fell right into our alley for this research. Right here is a quick summary comparison of the two between the PennDOT study and typical VDOT subgrade and pavements. You can see the subgrade soil is very similar, and the aggregate is also very similar, probably similar to your DOT specifications as well. The pavement structure, however, for the PennDOT study was somewhat thicker than the two cases that we came up with earlier. You can see the aggregate is basically the same, 5 and 8 inches at VDOT versus 6 in the PennDOT study, but the asphalt is a little thicker, 8.5 inches for PennDOT versus our very thin 1.5 inches and 6 inches for our secondary pavements. This graph illustrates how we took into account the differing asphalt layers between PennDOT's study and our two pavement design structure cases. The Kermani easels there on the right is the PennDOT study. We interpolated the thinnest VDOT pavement on the left and the thicker VDOT pavement in the middle. So these gave us our contamination rates. But in order to bracket the real world contamination rate and make sure that our study was broad enough, we actually used the equivalent of 1 inch of aggregate contamination per 5 years, per 10 years, and per 20 years. Now that we have our initial pavement designs and contamination rates, the next step is to do the pavement design runs. The first step is to increase the traffic level by the 2% growth rate each year. Then we reduce the structural coefficients of the asphalt layers to capture that deterioration based on the curves we just saw. The third step is to reduce the aggregate layers for the cases where no geotextile separator is used. For cases where the geotextile separator is used, obviously there's no reduction in the aggregate layer. And finally, we iteratively perform pavement designs to back calculate the estimated remaining design life. This table provides an example of a pavement case that was not constructed with geotextile separator, so contamination is happening. Also, the DOT has not performed any preventative maintenance. This is our thinnest pavement, the AADT 155, and the greatest contamination rate, 0.2 inch per year or 1 inch every 5 years. The pavement design back calculations that we just looked at provide the estimated remaining design life column on the left. The SSC column on the right is the surface structural coefficient based on the deterioration curves we just saw. So as the AADT, as the traffic goes up 2% per year, we can see the asphalt surface layer deteriorate as it ages. So for 2035, as an example, the SSC is 0.358. It's greater than 0.3, which is the cutoff we determined for maintenance operations. The estimated remaining design life, however, is 2.8, which is less than 5 years. We're looking at this in 5-year increments. So the maintenance decision at that point is to patch because the surface is relatively good, and normally at a DOT that is what would occur. It's not always by the book. 5 years later, in 2040, now the surface has dropped below that 0.3 threshold. The ERDL is very low, so the maintenance decision is to overlay. And typically that is how DOTs operate. We'll overlay much quicker than we'll reconstruct. So after that 1.5 inch overlay, our estimated remaining design life is now 11.4 years. If we drop down all the way to 2065, however, the surface is still actually pretty good, but our remaining design life is so low that an overlay will no longer give us an estimated remaining design life of 5 years. It can't get to 2070, so at that point we have to rebuild. We also calculate the ERDL at the very end, the 50th year in 2070, and that will go into some of our salvage value calculations. Another important aspect of our life cycle cost analysis are the materials costs. The example shown here is for geotextile separator by square yard, depending on the quantity. This data was taken from VDOT bid data from 2008 to 2018, and we did the same thing for all of the materials used in the pavement design and any maintenance. Another innovative aspect of this LCCA, we also included maintenance of traffic costs, pavement markings, guardrail, inspection, any ancillary costs that are not usually captured in a life cycle cost analysis to make it more applicable to real world VDOT projects. One thing to note, this is the graph here shows installed cost of geotextile, not just material cost. Now that we have a maintenance schedule for each of our pavement designs, different pavement cases, and all of our variables, we can easily calculate our life cycle costs. However, the question remains what to do with that salvage value at the end. VDOT manual of instructions would tell you ignore salvage value, but we're trying to be as real world and as detailed as possible. When you have a pavement at the end of year 50 that is in excellent condition, you think of that more of as an asset. When that pavement is distressed, you've gotten to year 2070, but it's not in very good condition, you think of that more as a maintenance liability. So in our life cycle cost analysis, we looked at two different options, that the estimated remaining design life is an asset, and one in where that's actually not an asset but a normalized liability. The two methods for terminating the pavement life cycle are different in a key way. The salvage value is subtracted from the total discounted cost calculated in the LCCA. The normalized liability is actually added to that total discounted cost because it is a maintenance liability moving forward. The salvage value is easily calculated by taking the estimated remaining design life, dividing by the 20-year pavement design life, multiplying that by a constant cost of a 20-year pavement design. The normalized liability is calculated by designing a 20-year pavement design, what we call the terminal pavement design, designing a 20-year pavement design based on the conditions of the pavement structure at year 50. These tables show the raw results of all life cycle cost analyses. The top two tables show the thin pavement, the 155 AADT, the bottom, the thicker VDOT pavement, the 1500 AADT. The left tables were calculated using a discount rate of 1.5%, the right a 4% discount rate. Each table is divided into two sets of 3 columns. The left were calculated based on salvage value. The right calculated based on the terminal pavement design or normalized liability. The bottom 2 rows of each table show differences between pavement designs with and without preventative maintenance. So the top row, PM, we used preventative maintenance. Bottom, no PM, no preventative maintenance by the DOT. Basically in these tables, the shaded cells show savings. The main variable is the contamination rate. So for instance, in the lowest contamination rate, 0.05 inch per year, or 1 inch over 20 years, those do not show any benefit to using a geotextile separator. But for the rest of the cases where contamination rate is reasonable, the geotextile separator shows a remarkable benefit. These tables consolidate the results from the previous slide to compare geotextile versus not using a geotextile separator. This includes all the variables that we had in our study: thin versus thick, low volume pavements, using a geotextile separator versus not, using preventative maintenance versus not, all three contamination rates, both discount rates, and both salvage methods. Each cell is the ratio between using a geotextile over not using a geotextile. So values below 100% indicate savings by utilizing a geotextile separator. Again, only the lowest contamination rate shows no appreciable benefit by using a geotextile separator, but all of the other cases do. So in conclusion, pavements with geotextile separators are expected to be cost-effective and outperform pavements without geotextile separator layers. This is regardless of pavement thickness or traffic volume, whether preventative maintenance is performed or not, and at various discount rates. Looking at this information another way, there is a significant life cycle cost advantage to utilizing geotextile separators. These outperform pavements without geotextile, even if preventative maintenance is performed. If preventative maintenance is not performed, geotextile separator cost advantage increases. This study also showed that the life cycle cost of geotextile decreases with decreasing contamination rate, although the cost of geotextile is a relatively minor one to ensure the subbase aggregate layer continues to perform properly. With a competent aggregate layer, only superficial maintenance is required. It should also be noted that the loss of permeability in the aggregate layer due to subgrade fine contamination was not included in this study, although it is expected that this will also affect pavement life. As we've noted, current pavement design methods do not consider aggregate contamination. Thus, some pavements designed using these methods may deteriorate at faster rates than expected, increasing their life cycle maintenance costs. Aggregate layers protected by geotextile separators are more likely to be preserved and reused at the end of the pavement structure's life. This concludes my presentation. Thank you for listening. I hope you found this interesting. If you'd like more information on this study, the full report is available through the Virginia Transportation Research Council in Report 20-R8. Thanks again to my co-author, Audrey Maruza, the Virginia Transportation Research Council, and VDOT for sponsoring this research. Have a great day.